Day 161, Photoelectric Effect, examples 22 and 24 for the homework. Hints, we have a ruby laser, doesn't really matter, it's a red laser. The main thing here is it's a wavelength of 694 nanometers, and what we can do here, like in previous problems, we can figure out the frequency of this particular photon. Since we have V equals lambda f, and it's a photon, speed of light, 3 times 10 to the 8th meters per second equals 694 times 10 to the negative 9th meters times the frequency, and you will calculate the frequency of this photon. And if you have the frequency of this photon, you can use E equals HF to get the energy of this photon. So you take your answer for the frequency, plug it in there, plug in your Planck's constant, and you'll get an energy for these photons of some value. And that I would probably do it in joules. All right, that gives you the energy of the photon. Now, from previous units, we know that power equals energy over time. And they're telling you the power of this beam is 1.8 megawatts. That's 1.8 times 10 to the 6th joules per second equals the energy over the time of 0.4 times 10 to the negative 6, that's microseconds. So that will give you the total energy, I'll call that E total, for this pulse. On the left-hand side over here, this is the energy of the photon. This is the energy of each individual photon. So you'll have that, and you'll have the total energy, and I'll leave it up to your creative abilities to calculate then, using those two numbers, how many photons it takes to make that total amount of energy. All right, let's go to example 24. Once again, we're given the wavelength for the threshold. Now, just to recap, the energy of the threshold photons, or the frequency, but the energy in particular, energy of threshold will coincide with, or will equal or match, the work function for the particular surface we're dealing with. All right, so like the last problem, or like many of the problems, we can figure out the energy of these particular photons. We use V equals lambda f, just like we did in many of the previous problems. 3 times 10 to the 8th equals 420 times 10 to the negative 9th times the frequency. So we get the frequency of these threshold photons. And then we find the energy of these threshold photons using E equals HF once again. Take your answer from part 1 here, plug it in for F, and you get the energy of these photons. These are the threshold photons. Okay? And we also have the electrons coming off with a velocity, giving them kinetic energy. In other words, we can calculate the kinetic energy, the maximum kinetic energy, because these are the highest speed electrons, by plugging into 1/2 mv squared. And once again, the mass of the electrons is given. So the kinetic energy max is 1/2 times 9.11 times 10 to the negative 31st. That's given, negative 31st kilograms, times that velocity, 6 times 10 to the 5th. Quantity squared, squaring the speed. So you get a kinetic energy maximum for your photo-emitted electrons, equals some number. Okay, well, the photoelectric effect equation is this. Energy of the high energy photons, not the threshold photons, and that's the biggest point of confusion when you're first starting out here, is you have the energy of the threshold photons, the ones that would just barely cause photo emission, and then you have the high energy photons that are above the work function that then contribute to not only getting the electrons loose by the work function, but also then the excess energy going to the kinetic energy. So the energy of the photons in particular that we're looking to find is equal to the energy, the work function, plus K E max. And I would put these all in, well, the KE max is going to come out in joules. You probably want to have your threshold photons in joules as well to make this a little bit easier going forward, or right now. So you have your kinetic energy of your photon, or your electrons, and the energy of the threshold photons go for the work function. So if you add those together, you get the energy of the photons in particular that we're looking for to produce these electrons. So once you have that figured out, then you do E equals HF. That energy right here will go into here, and use Planck's constant to get the frequency of these particular high energy photons. And once you have the frequency of those photons, then you would use the final equation, V equals lambda F. You would take that frequency you just calculated and plug it into here, and plug in the velocity of light, 3 times 10 to the 8th meters per second for the photons, to get the wavelength of the photons that are producing these electrons.